Hello everyone, how are you? So today we are going to cover the chapter 8, which is friction. This table shows you how many chapters we completed so far. So we completed chapter 6 last week, and thank you for your hard working on the midterm exam 2, which was on the Tuesday. I really appreciate your hard working, and most of the students got a very good job in the midterm exam too. Now we have remaining two more chapters, friction and the center of gravity. I will try to finish these two chapters by the end of this semester. Okay, so friction is a very interesting topic, and we never learned this topic before. Um, let's see dry frictions, characteristics of dry friction. Today we have two learning goals. The first one is I want you to understand the characteristics of dry friction. Next goal is solving problems involving frictions. Have you ever pulled the refrigerator using your rope, or have you ever pushed the refrigerator with your hands? Um, it's really hard to move because the refrigerator has a lot of weight, right? It's very heavy. Because it's very heavy, then there are a lot of frictions between the surface, floor and refrigerators. Obviously, refrigerator is made by steel. Steel has a high frictional coefficient compared to other materials. So we will see that part later. But it depending on the material, also the frictional force is depending on the weight. More clearly, it depending on the normal force, okay, created by the weight. So friction force is if you pulling this object to some directions, then the frictional force has opposite directions. Okay, it always has opposite directions, preventing the slipping the bodies. Okay. So dry friction, we are talking about the dry frictions, which is there is a weight and there is a push or pulling forces horizontally. Then if you microscope the surface, there are the very some uneven contact surfaces, but the upper part is, we assume that this is rigid, but the bottom part is surface is deformable. So we call this is a dry frictions. Okay, if you look at each contact point, there is a normal force, frictional force, normal force, frictional force. The textbook shows you delta F1, delta normal 1, delta F2, delta normal 2. But we learned distributed loading. Okay, even though the contact surface is not very even and smooth, we think about, oh, okay, we learned the distributed loading. There is a distributed load, so we can simplify the problem with a one normal force and one frictional force. Let's assume that the surface contact surface is very even and smooth, so we have only one normal force and one frictional force. Okay, so here is a simple box. Obviously box has a weight, and the weight, because of the weight, we have a normal force from the surface. Okay, the normal force can be located in the center, but in the friction problems, we may need to think a little bit differently, because there is a contact point. Okay, contact point. It can be in the middle of the object, or it can be slightly off from the centers. It depending on the um, it depending on the calculations. So we will see how to find the distance from the center to the contact points. And the contact point is very important. If the this point is in the within this range, then this gonna be slippery. But what about the point is very far, and this is beyond the box width and this much, then this box will not slip, this box will tipping. Okay, we will learn this concept later, but anyway, there is a weight and the normal forces. So this is the external force. We push or pulling this object, then there is a frictional force. Because this object is not moving, okay, we are dealing with the object with no motion right now. Okay, it's not a dynamics, it's a statics. So we can apply these three equations: sigma fx equals 0, sigma fy equals 0. Any points, the moment should be equal to 0. Okay, so let's look at this. Sigma fx should be equal to 0. That means your pulling or pushing force is equal to the frictional force. Okay, very simple, right? Because this object is not moving, translational moving, so it's not moving. That means frictional force and your pulling force are the same. How about the vertical directions? Since we have to satisfy these equations, so minus w, because the direction is the downward direction, minus w plus n should be equal to 0. So w is equal to n, just opposite directions. How about the moment? At any point, if you calculate the moment at point O, that should be equal to 0. If you see that here we have a contact surface point O, and we have a weight, and this pulling force create the moment, rotations. We have dimensions here. This is a half of the height, and this x is a horizontal distance from the centers. So if you look at the equation, minus, because this one creates the clockwise rotation, minus p times height over 2 plus weight times x is equal to 0, because w create counterclockwise rotation. That's why the sign is positive. Okay, so we have a 3 equation to solve the problem. Oh, that's great. So if we have 3 unknowns, it's pretty solvable with these 3 equation. And in this chapter, I'm going to show you one more equations. Okay, that's the friction equation. We will see later. The question is, so pulling force is equal to frictional force. Okay, just like what we saw. But what about the pulling force is greater than the frictional force? What happened? Then the object will move. You know what I'm saying? So if the push or pulling force is greater than the frictional force, then the object will move. But it's less than the frictional force. Pulling force is less than the frictional force, then it will not move. Okay? So here we have a simple chart. The x-axis shows your pushing force, and the y-axis shows frictional force. If the pulling force and the pushing force is equal, they are same with 45 degree, that means the increment is the same, okay? Then there is no motions, okay? But once your pulling force reach the maximum frictional force that object has. Each object has different frictional coefficient, but that means each object has different the frictional maximum frictional force. Okay, so once your pulling force reach to the frictional force, the maximum frictional force, then it will start to move. Okay, so there is a motions. We call the red part, which means this part. There is no motion, and we have a maximum frictional force, and this K indicating kinetics. That means the object is moving. Okay, so we have a two part. One is a static frictional force, and the other one is a kinetic frictional force. The question is, does frictional force, static frictional force, is always greater than the kinetic frictional force? Yes. Static frictional force is always greater than kinetic frictional force. Okay. In the simple word, you have to remember that impending motions. What does it mean? Impending motion means once your pulling force is reached to the static frictional force, that means the object will begin to move. Okay, at that moment we said that is impending motions. Okay. So this is another equilibrium equations for you guys. We never learned this concept before. This is a pretty new concept because of frictions. Static frictional force is equal to mu s times normal force. What is mu s? Mu s is coefficient of static frictions. If you think about what else? If you think about aluminums or rubber or steel, they have on the coefficient, static frictions coefficients. Okay, so we have this equation, which is a force equation. First one is sigma fx should be equal to 0. Second one is sigma fy should be equal to 0. And the third one is sigma any point moment should be equal to 0. And the last one is frictional force. We are dealing with static frictional force is equal to mu s times the weight, normal force. Okay. I think this is way too much information, but if you see that there is a normal force and frictional force here, there is a relative force here, which is, let's say, which is a resultant. This is R static force, and here we have some angle information, that is a psi. If you see that tangent psi is actually friction S over N, normal force. And we know that friction S is equal to mu Sn. That means mu S is equal to tangent psi. So this angle is affecting to the coefficient, frictional coefficient. If the angle is very big, okay, very big, that means it has a very high frictional coefficients. For example, this is the table. It's kind of a reference. If you are, screw up the two different objects like aluminum versus aluminum, it has static frictional coefficient. You can find this information on Google. Okay, so you can see that it's very high. It's more than 1, okay, 1.35. How about the rubber versus rubber? Rubber versus rubber is 1.16. Oh, it's not that high compared to aluminum versus aluminum. Which one has the lowest coefficient? This one. This one is 0.2. Okay, it's a brake material and cast iron. Okay, has a lowest static frictional coefficient. If we use some lubricated materials, then this static frictional coefficient will significantly dropped. Okay, so this is just information for you. Okay. All right. Now let's solve this problem.